Hello. Today we're going to talk about levers as a lesson which bridges our unit on forces and our next unit about torque and rotation. To begin, I thought I would share a quote from our friend Archimedes. He once said, "If you give me a lever long enough and a fulcrum on which to place it, I shall move the world." In this video, we will learn why that might be theoretically possible. A lever is simply an example of a simple machine, which is a force multiplier. By adjusting the distances away from a pivot point or an axis of rotation that you apply the forces, you can either exert a greater force on an object than you might otherwise, or you can apply a weaker force over a greater distance than possible. There are several different classes of levers, which I hope one of you guys will explain to the class later this week, which essentially boil down to the arrangement and the direction of the forces relative to that axis of rotation, which all provide different types of advantages. Now, all of these types of levers follow this simple law that Archimedes might have used, which says that the force times the distance away from a pivot point equals a different force times its distance away from the pivot point, or FL equals FL. As you can see, the F's are forces that are perpendicular to the bar or lever, and L is the distance away from the pivot point. So let's look at some examples. First of all, how far away should we apply a 45 Newton object if it's sitting opposite of a 30 Newton object that's 1.8 meters away from the pivot point? Now, you might remember back in elementary school going on the teeter-totter. If you had to try to teeter-totter with somebody who was heavier or lighter than you, remember that you had to scooch forward or back a bit on the teeter-totter to balance things properly. Well, that's essentially what we've got here. Let's draw a lever, and we'll put in a fulcrum. And on this side, we'll hang a 45 Newton object. So I'll just say 45 newtons. And it is opposite a 30 Newton object, which is 1.8 meters away. So I'll draw 30 newtons, and it's 1.8 meters away. And we want to know how far away does this need to be. So I remember from elementary school, the bigger kids usually had to scooch closer to the center than the smaller kids. So it looks like my drawing isn't to scale, but we'll calculate things anyways. The rule says that the force, or 45, times the distance away, which we call x, has to equal the other force, which is 30 newtons, times its distance, 1.8. Now we'll learn in our next video about torque that there are standard units that you can apply here, but this rule can apply with any units, pounds, newtons, tons, ounces, and any distance units, as long as we're consistent. So this is a simple enough equation to solve. Just divide both sides by 45, and the distance away from the pivot point is whatever 30 times 1.8 divided by 45 is, which I calculate out to be 1.2 meters. In another example over here, you see a lever that is somehow hanging by a hinge, and there's a weight tied on one side, and then there's a support cable here that's holding it in place. And I'd like to figure out how much tension is in this string if 150 newtons is the weight on the end. So, once again, we will use Archimedes' formula, and the force is the tension, and the distance away from the pivot point for that tension is 0.8 meters. So, and on the other side, the force is 150 newtons. And its distance away from the pivot point is not 2.1, but it's the total, 0.8 plus 2.1, or 2.9 meters. And again, this is a relatively easy one to solve. Just divide both sides by 0.8. Don't worry, they'll get more difficult if you're wondering. And I get for that one 150 times 2.9 divided by 0.8 is roughly 540 newtons. I rounded to 2 significant digits because that's how much we knew originally. So I got 543.75 if you were curious. Alright, now it's your turn. Suppose there's a 1.7 meter long stork who's flying through the air carrying an 8-pound baby in his mouth. Let's pretend that baby is located 1.2 meters in front of the stork's center of mass. To keep from rotating forward, the stork must also be holding some sort of counterweight in his feet. How much counterweight must the stork carry in order for it to stay balanced? Why don't you press pause and see how much progress you can make, and when you're ready, hit play and I'll show you how to finish. So, the stork is 1.7 meters tall and has a center of mass which from the details looks to be 1.2 meters away from the baby. So, baby pulling down at 8 pounds, 1.2 meters away. On the other side, there must be a counterweight. That counterweight, because the total distance is 1.7 meters, must be located half of a meter away. And so we can set up the formula. 8 pounds times 1.2 meters is equal to the counterweight times 0.5 meters. If we divide both sides by 0.5, that's the same thing as multiplying both sides by 2. And we get that the counterweight must be equal to 19.2 pounds. They don't usually show that in the pictures they provide for storks, do they?